Just a reminder again that there will be the take-home exam this weekend. It'll probably be unlocked Saturday morning, and then it will lock Sunday night. So you have the full Saturday, full Sunday. It'll be on energy and momentum, the whole shebang. It's a big unit. I'd say nearly as big as the whole force, all the forces. That was a massive unit too. A lot of material in there, but that's what it is. It's a big unit. Anticipate that you should stick away some hours to do it. It'll probably be 40 multiple choice questions. I mean, it depends, right? I mean, depends on the student. Just remember that you need to get through a similar exam in 3 hours, right? It's 3 hours. Mine will be less because I'm not going to give you 50 multiple choice and 3 free response. I'll probably give you 40 multiple choice and 2 free response. But, you know, I'm giving you the 2 hours. I mean, I'm giving you the 2 days because if the assumption is that every student wants to learn, it's a wonderful assumption in theory, just in general, not even referencing an AP class, just as a teacher. If the assumption is that every student that you have wants to learn and that every student will put in their full effort no matter what, then take-home exams is the way to go. Because then students are given an opportunity to figure out stuff that they don't already learn, don't quite know yet, and they'll have a whole 2 days to figure it out. And then they can actually come out of the exam knowing some things that they would not have been able to demonstrate an understanding of had they been in class. So it can actually be an opportunity to learn, which puts the general model of testing on its head, because generally the model of testing is that you put kids under pressure, you give them 30 minutes, and you know what you know, and that's it. If you didn't do well enough, well, study more. Well, come after school. We all know that that's typically how it is in schools. Which my son, he just cheated. He just cheated for the first time. 4th grade, we got the email that he cheated on a math test. Now he's great at math. He's great at math. His thing is math. And we're like, so why did you cheat, bud? Like, so why did you do that? Well, everybody else is, finishing before me. Everybody else is finishing so quickly. And it made me, and I was stuck on this one problem. I didn't know how to do it. Like, that's okay. Like, did you ask for help? Like, you're a 4th grader. Your teacher probably would offer some help to you. No, I didn't. She was busy. All right. I thought to myself, so what did you do? I took out one of my sheets, tried to hide it under my desk, and then someone saw me. I thought, what a shame, because he feels the pressure. He feels the pressure to perform on a test already and only in 4th grade and doing things like that, where I thought, if it was more relaxed of an atmosphere, maybe he wouldn't have felt that way. I'm not giving him an excuse. He shouldn't be doing it in the first place. But it's just the way that kids are brought up in schooling, right? This idea of the test. Right? It's like he already feels it in 4th grade. I said, obviously you shouldn't be cheating, and the whole point of a test is so that we better understand what you know, and you better understand what you understand. So we and you both know what you know and what you don't know, because then we can better address the things you don't know. If you cheat, then you fooled us all into thinking that you know some part of it that you actually don't know. And when we get your results, we look at it and think, wow, he's great, he's doing wonderful. And then when there's a standardized test, doesn't come through, right? Then parents are scratching their head. What's going on here? I said, well, it's better that you just do the best you can, ask for help. And if you don't understand something, that's okay, because it's an opportunity for you to still learn. The whole point of everything, all of this, is that you learn something. So, all that said, putting a test, giving students a test at home to AP students who generally are those students that I described. They do want to learn. They do want to put in their full effort. They do want to get A's. Not a terrible choice, in my opinion. Did anybody else give you take-home exams? A single other teacher? What's your choice? All right. Let's begin. Rotational kinematics is the new unit. Let me just pull up my smartboard and get that going. Oh wait, he's got this one. And I also said to my son, like, let me tell you a secret, little buddy. Usually the people that are handing it in first have the poorest grades. Usually the best students in class hand it in last. Oh, that can't be true. I said, I've been teaching for 15 years. You're 10 years old. You don't think I know what I'm talking about? You don't think that I know what I'm talking about regarding this particular thing? That the best students, not only the best skilled and most knowledgeable, but the ones that care the most are the ones that will puzzle on that one problem for 40 minutes before they decide, as the last student, potentially even the last student that even asks for more time after school, right? So that they can get that problem in and try their best to do it. And I said, so your view, I said, I remember being the kid. I remember being your age thinking the same thing. If people are finishing before me, they must be smarter than me. They must have figured it out. I was like, let me share that secret with you. There's also students that don't care, that they did the best they could. They filled out half of them, and they're not the kind of personality that's going to sit and stare at those other 5 problems for another hour. They're just going to hand it in. And you think, oh, I don't know anything. And I'm like, you being the one that cared the most, often, it's not always the case, but usually those are the students that are the last to hand it in. It's like, it's interesting, like the perspective, right, of the student versus what the teacher sees. Usually the best students, the highest performing students are usually the last ones to turn it in. So, interesting. Usually, not always, but usually. All right. So let me just hit this button and we can go. All right, so we're doing rotational kinematics. I can find the marker. Okay. So the new unit is rotation. It's a biggie. I will tell you right now, it's a biggie. And the first section we're going to tackle is called rotational. Oh, am I sharing my screen?
Yes.
Oh, yeah. Okay. And wait, I always just never remember because I always have my side conversations. And I can't remember. Did I hit record? Yeah, I did. Okay, go back. Rotational kinematics. Then there's Newton's laws. I'm just giving you just a breakdown of this whole unit. Then there's rotational momentum. Then there's rotational energy. So we essentially have to revisit all of the things we've talked about and then figure out how do those apply for things that are spinning. When we say rotating, we're talking about spinning. We're not talking about circular motion. We're not talking about the planet that goes around the sun, where we would actually be talking about the planet spinning on its axis. We would actually be referring to the spinning Earth that causes a day, not the revolution. That's circular motion. We've done that already. So just to make sure you're clear, when I say rotation, I'm talking about something that's spinning, like a basketball on somebody's finger. That's what we're talking about. These are all the sections. Thankfully, all of the stuff that you know, we get to use. It's all the same ideas. It's even all the same formulas, which is wonderful. It's just essentially a transfer of very similar stuff, again, a transfer of stuff, ideas and equations, straight over to something that's similar but a little different, but thankfully all of the stuff applies. It's wonderful. So today is our day to deal with step 1, rotational kinematics. So let's start with something we know before. You should always do that. You should always remind somebody of something they know. Am I working? Yeah. Before you teach them something they don't know. I mean, not randomly, something that's connected. Bless you. So let's look at linear kinematics. And let us compare that to, well, rotational kinematics right on the board. So linear kinematics is linear. The word linear means that stuff moves along a straight line from point A to point B. Linear meaning, right, the shape of the path is a line. If something physically moves from point A to point B. It can go at a constant speed. It can go at a fast constant speed. It can go at a slow constant speed. It can accelerate while it goes from point A to point B. It can decelerate, slow down, like a car skidding as it goes from point A to point B. It can go from point A to point B and then turn around and go back from point B back to point A. It's all included. It's all included in linear motion because the path, the shape of the path is a line. It can go up and down, throwing a basketball up and it coming back down, linear motion. Throwing something sideways, anything. As long as the shape is a straight line, it falls under linear kinematics. For rotational kinematics, we're now referencing something that rotates around some axis. So this is usually called the axis of rotation. Doesn't have to be drawn that way. If it was, the Earth, then we know the Earth is kind of tilted at that 23-degree angle. Then this would be the axis of rotation. It's an imaginary axis that the Earth spins around. If it was somebody just spinning a basketball on their finger, and the basketball is this is their finger down here, then the axis of rotation would be straight through the center of the basketball. It's just something that something spins around. It doesn't have to be a real thing. It's just an idea that all the points revolve around that one central line called an axis of rotation. So what we're talking about is, well, we can still say something moves from point A to point B. Let's try. Something on this disk, so let's just think of it as like a disk, and something's causing it to spin, which, by the way, we don't address that until we go into Newton's laws. If you think about how physics is taught in kinematics, linear kinematics, we start with just teaching students how to quantify and model motion in general, constant speed motion, accelerated motion. How do we identify it? How do we distinguish them? How do we model them with equations? No discussion about what causes motion. We don't deal with that until later. You'd think that actually maybe you should start with describing why things move in the first place, which would actually mean that you'd start the year teaching Newton's laws, that you teach with forces being balanced and unbalanced that cause motion, and then go into describing the kinds of motion that you see. But they don't. For 100 years, physics has always done, let's just talk about motion in the beginning, then we'll talk about why things move after with Newton's laws. And they all certainly all connected. The same thing, we're following the same pattern. We're referencing something that's spinning. Why it spins in the first place, we talk about in the next unit, which is Newton's laws, which is called torque. When you apply a torque to something, it's a force that essentially is in this direction, which you don't have to write this down. This is the next unit. I'm just explaining that when you grab something, like if there was a rope here and you pulled it, it would start, well, it's toilet paper, right? That's actually what a toilet paper roll does, right? If you grab it and you pull it, it'll start to rotate. And that force is called a torque. But we deal with that later. So in all of our discussions, we don't ask about what's causing it to turn. We just said, we'll talk about that later. We're just going to reference something that's turning or spinning. And how do we quantify its motion in a similar way to what we had on the left. So let's just imagine there's a piece of tape that you stick on this wheel. Because we're not necessarily interested in the disc itself, though we sort of are. When we're tracking something's motion, you have to pick a spot on the disc and say that I'm gonna be able to try to quantify how this little, it could be a marker. You just take a red marker and mark something red on it. As this thing spins, can you technically keep track of its motion? You're watching that red dot as it spins around. I always call it the piece of tape. This can still be point A, and now it rotates to point B. Right? So there's a rotational effect now, causing it to go from point A to point B. Remember that in this case, on the linear kinematics, it can move at a constant speed. If it was a car, I don't know, this car or something, going from A to B, it could go at a constant speed. It can speed up, or it can slow down. Accelerate, decelerate, constant speed. Those are all possible motions that we already talked about quite a bit. Same thing over here. If you tracked the motion of this thing that was spinning, and we're actually going to do some labs for sure. There's some great Pivot interactive labs that are all referenced to this disk and things that are spinning to help you understand what I'm referencing. But if I just threw you into it without anything, it wouldn't go as well. It's better to teach something first. We'll do that after, some other day. But if you watch this thing going around, like you'll do with the video frame at a time, there's a possibility that this thing is rotating at a constant speed. I'll give more pictures of what that means in a moment. But when we say speed, now we use the word rotational. We say constant rotational speed. I'll explain again what that means. Just know that that's the vocabulary we use. It can move at a constant rotational speed. It can have a rotational acceleration as well. So I mean, I could have over here, I suppose, to try to stay consistent. I could have said, really, there's constant speed motion, and then there's accelerated motion. And when we break down accelerated motion in physics, we see that there's two types that are considered acceleration, which one is speeding up, and the other is slowing down. Well, same thing. With a rotational acceleration, you can have it where it speeds up in its rotation, spinning more and more quickly, like a basketball on your finger. Each time you tap that thing, when someone tries to get the basketball spinning on their finger, it starts off with a slow speed. Each tap provides a little bit of a torque, and that causes the rotational speed to increase. And if they went tap, 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 tap really fast, keep tapping with their fingers, with their hand, if you've seen people spin the ball before, it can get rotating very, very fast, right? That time where the rotation speed keeps getting faster and faster and faster is considered a rotational acceleration. Even a washing machine, when it goes into spin cycle, right? It starts off slow, and then it gains speed and faster and faster and faster. And after a few seconds, that thing is humming. Have you guys seen these things on spin cycle? You're close. God, I don't even know how many rotations that's doing per second, but it's a fast rotational speed. And during the time that it's getting up to that maximum rotation speed, we call that a rotational acceleration. So it can either be speeding up or slowing down. Like the basket I just mentioned in the washing machine, after it's done with that cycle, it then shuts the motor off, and that thing rotates and rotates and rotates, but it actually starts slowing its rotational speed down, little less and little less rotational speed until finally it stops, right? That would be an example of a rotational deceleration, slowing down. Okay, now let's go on to the next idea. Let's look at constant rotational speed. Like just to get a sense as to what that means. Oh, well, I'm doing it backwards. Sorry. Let's do constant speed the way we always did, and then let's compare it to constant rotational speed. For a regular linear motion, for something that's moving at a constant speed, we say that something moves equal distance per second, right? If this is where it is after 1 second, it's at this point, 2 seconds, it's here, and 3 seconds, it's here. We can identify constant speed motion by indicating that these are all equidistant. If they're equidistant, then you know that it's moving equal distance per second, and that's actually what constant speed is defined as, something that moves an equal distance each second. If they're wide gaps in between each, then it's moving fast, covering a greater distance each second. If they're closer together, like for an ant, if you did this and put down a little mark every second while an ant crawls on the driveway, they'd be close together. Still be equal, indicating the ant still probably crawls at a constant speed, but close together dots means it's moving at a constant speed, a constant slow speed, I meant to say. How would that look for rotation? If this is our point right here, and let's just call this like, I don't know. Well, I'll just keep it the way I have, 0 seconds, 1 second, 2 seconds. So let's just say this is our tape. And I don't know, it doesn't have to be on the edge. I mean, it can be anywhere. Yeah, I'll leave it on the edge. Just imagine that you put the piece of tape on the edge. If this is where it is after 0 seconds, and this is where the piece of tape is after 1 second, and this is where it is after 2 seconds, and this is where it is after 3 seconds. Oh, it looks like a pizza. Oh, not quite. 1, 2, 4 slices is supposed to be half of a pizza. I'm not a good pizza cutter. There we go, 4 slices. Then this would be a good way of identifying constant speed motion. Now, the reason is we're not going to reference distance anymore like we used to. We used to reference some distance along this straight line. Now we're going to be referencing angles. This whole unit is all about using the protractor and the angle as a measurement on where it is on the circle. So let's just say that this was, well, 180 divided by 4. What does that come out as? 40, these are supposed to be, although it doesn't really look, it's supposed to be 45 degrees. This should be straight up. Anyways, you get the point. These would be all 45 degrees. So if it's essentially moving an equal angle of 45 degrees each second, then that would be your clue as to the fact that this thing is rotating at a constant angular speed. Similar, again, it's the idea of a motion map, but in a circle sense now. So this would be constant because it rotates an equal angle each second. That's the big idea for what we call constant rotational speed. For the linear case, of course, it moves just a physical, equal, linear distance each second. Okay. So what I'm kind of hinting at is that we don't use x anymore. We don't use x, which was the symbol for position, right? We used x. You could technically use y. In college, when something's going up and down, they take away x and they put y because the y-axis goes up and down. It doesn't matter. It's the same idea. In your textbooks, for whatever reason, I don't think they show y. So whatever, x. Position, but we use the position symbol x. Anybody want to guess what the symbol is going to be over here? Because here I'd say that this is at a position of 45 degrees. Here it's at a position of, which is not straight up, it should be. It's at a position of 90 degrees. Here it's at a position of 135 degrees. Here it's at the piece of tape, again, is at a position of 180 degrees. So we're going to use angle as a reference. Yep, theta. So the new symbol that we use is theta. We don't use x anymore. Theta is the symbol. Is considered the, let me erase some of this, make space. Theta it's called an angular position. Now I want you to know that we use that word angular and rotational kind of in the same sentences. Some people say something has a rotational speed, other people say it has an angular speed. Angular just means that it rotates through an angle. Not angular like an angular rock, which has like jagged edges. No, angular in physics and what we're talking about, an angular rotation or angular speed means it's rotating like a wheel through an angle. Each revolution is 360 degrees. So we use theta as the symbol. Okay, let's go on to the next idea. If we had x, which was position, and it was measured in meters, now we have theta, which is considered angular position. This other one would be linear position. And the unit would be, now, I learned in the last class that some of you have learned radians. Ashley, you probably have learned radians because you're of your ages. But some of you, like Zoe, probably not. You've never heard of radians. So on another lesson, I have to teach the class what radians is. Radians is just another unit for angle. Like centimeters is another unit for it, like for distance. You can measure it inches and feet and whatever unit you use to measure something's length, it doesn't really matter. Concept's the same. Each unit might have a physical different size, like an inch and a centimeter are not the same length. For angle, there's two different units that are commonly used. One is degrees, which you're certainly familiar with. The other is called radians. And the SI unit used in physics and engineering is actually radians. It's not complicated. I can easily teach it in 20 minutes. I'm not going to today. But just know that for today's lessons, I'm going to reference it as radians. But when you see radians, just think degrees, because conceptually it's a similar idea, just a different word. I'll give you just a quick sense that what we call, when we say pi radians is 90 degrees. Or, I didn't mean to say that, pi divided by 2. Pi divided by 2 radians is 90 degrees. Or when we say pi radians, that's the same as 180 degrees. That's like saying, 2 centimeters is the same as 1 inch, right? So this amount of centimeters is equal to this amount of inches. It's the same idea. We have this other unit called radians, and there's some amount, because pi is actually a number, right? 3.14 radians is equivalent to 180 degrees. Or pi over 2, I don't know, 1.57 or so. 1.57 radians is equal to 90 degrees. We write rad is equal to 90 degrees. Or what I just say, 3.14 rad or radians is equal to 180 degrees. Why and what radians means and where it comes from, I'll give it all in another lesson. It's not important right now. Just know that there's this other unit called radians, and it can be easily, you can easily go from degrees to radians and from radians back to degrees. A full circle all the way around, by the way, is 200, which is 360 degrees all the way around, is 2 pi. 2 pi radians. It has to do with geometry. You guys know pi comes from geometry with circles and all that stuff, so we'll get to that another day. So just know that when I reference angle, I'm going to write radians. Just think RAD. Teachers usually say rad, like 2 rad or 5 rad. It means radians, it's short. So the question is, what is the symbol for radians? It's RAD, which is short for radians, which, again, just think, it's like degrees. It's like degrees. Now let's think about what's the next, quantity in linear motion, v, right? And we would call that linear velocity. In fact, I don't want to talk about velocity because the direction doesn't matter right now. Let's just think of speed, linear speed. Units would be meters per second. How do we figure out what something's linear speed is? Well, technically, just in general, we would take, we would say speed is equal to distance divided by time. If you're looking at constant speed motion, right? If you can track how far it goes in distance, time how long it takes to go that, do distance divided by time, that should give you the speed, just for constant speed motion. So that means for this one, what we're going to call rotational speed, it's going to have to be similar because all the formulas are similar. But what are we going to place in place of d, distance? Yep, theta, it's the angle. How quickly it moves affects how much angle it rotates through. If this thing is rotating really fast, it could go around the whole 360 degrees in 1 second. If it's going really, like a wheel that's spinning really slowly, it might only go 45 degrees in 1 second. So that full angle that it rotates through is totally related to this rotational speed. So instead of d, we put theta here, and we would still time it. We'd time how long it takes to go through an angle. So this is the angle it rotates through in t seconds. We don't know it, you'd have to time it, right? Just like over here, this is the distance it travels. It moves. This is the distance it moves in t seconds. I mean, again, you'd have to time it. Measure the distance, measure the time, and do a ratio of distance divided by time. That'll give you the speed. So this new symbol is actually a W, and we say omega. Omega. Omega is a Greek letter. It's their W. I'll put that equation on the board a little later. Don't worry about that. But we call this rotational speed. And any guesses of what the units are going to be? Yeah, radians per second. Just think of like angle per second. How much angle it goes through per 1 second. Again, I'm putting rad for radians, and we'll certainly tackle that more. Let's just notice the similarities, right? Linear position was units of meters. Then we have meters per second. Same thing. We have some angle, this new thing called radians. But then the rotational speed is how much angle it goes through per second. We call that radians per second. That's similar to meters per second. All right, what's the next one? What's the next possibility? Well, I won't go to the next possibility. I will now actually leave that, leave this analogy right here. Omega, and actually I'm going to write another one. S equals d over t is kind of sloppy. I mean, it's just general idea, divide distance by time, but generally we would write v equals delta x over delta t to be a little more specific, where delta x represents the displacement, what we call linear displacement. How far was it displaced, linear in a linear sense, and then divide by delta t, how long it took to displace itself by that distance. Units of meters per second, because x is in meters, t is in seconds, so it should be meters per second, right, for units. What will it be over here for omega? Delta indicates you have to reference 2 points. This was x1, and this is x2, then we call this delta x, the change in position between those 2 points. For a circle, if the tape starts here, we call this theta 1, and then the tape is over here, and we call that theta 2, then the angle in between them is what we call delta theta. It's an interval. It's a change in its angular position. So it starts off at some position on the circle, ends up, you spin it a little bit, it ends up at another spot, you freeze the video, and then again, if you draw that angle, what you would just call it theta in geometry class, we're going to call it delta theta. It's a change in position, change in angular position. So this formula should be omega equals delta theta over delta t. And I'm going to give examples of that. You see how that works. You'd have to time it. You'd have to time how long it takes to go from one position to the second position along this circle. And you can do it in degrees. Maybe, well, I'll do that example now. Let's try that. So now let's do the example for constant rotational speed. The piece of tape goes from, here to, I don't know, here, where we still use this as 0 degrees. This is still considered 90 degrees. This is still considered 180 degrees. We still use the same system for angle, 270 degrees, and over here, all the way around, of course, is again 360 degrees. So let's just say it goes from, this position here at t equals 0 seconds, and we're just imagining something that's spinning. And that's our piece of tape. Our little black dot is our piece of tape. And then let's say at t equals 3 seconds later, it's over here. Maybe it's a giant merry-go-round, I don't know. Maybe you're looking down on a giant merry-go-round, and that black dot is, Dad's head. Dad's bald head, I suppose. And he goes from this position on the right, and then 3 seconds later, we take another snapshot with a drone or something, and he's over there. If someone says, what is the rotational speed? What would we do here? Well, let me give you this angle, and let's just say this is an angle of 135 degrees. What would we say theta initial is? 0 degrees. That's right, Jane. We'd say the initial position happened to be 0 degrees because he started on that spot. And then theta final will be, well, 135 degrees because we said that that's where the person is. Notice we're using the protractor as a measurement tool for its position as it goes around. So what would delta theta be? Delta anything is always final minus initial. Yep, you'd say its final theta was 135. Again, I know I'm using degrees and it's fine because I could still teach this whole lesson just talking degrees and mixing degrees and radians. So don't worry about that. Later, once I've done the radians lesson, everything is radians at that point. But no big deal. I'm using degrees right now. Okay, theta initial is 0. So what is the change in that angular position? It's the full amount, 135 degrees. Now you would have to time it. If this was a drone, watching this person go along the merry-go-round, you'd have to sit there and start your watch when the person was over here, stop your watch when the person is over here, and report the time. I don't know, let's just say, I had said it. I had said 3 seconds. So it took 3 seconds for this person to go all the way from the original spot to the final spot. So what would omega be? The rotational speed. Delta theta over delta t. The total angular change in position was 135 degrees. Divided by how many seconds? 3 seconds. What would I get when I do 135 divided by 3? 45. Yep, because 45, 90, 135. So that tells me, I'll run out of space, but I'll write it. I hate that thing pops out like that. That I have 45 degrees per 1 second. So I could certainly say that the angular speed, if I wanted to report it in degrees per second, and I'm allowed to do that, I'm just saying that most of the time we don't. We use radians, but it's a concept. It's an idea. Okay, that means per 1 second, this thing was moving. If it's a constant speed, right? Then that tells us where would it have been after 1 second? If we were to map that information onto this, well, if it's going 45 degrees per second and it started at 0 degrees, then 1 second later, it should have been here. 2 seconds later, it would have been here, right? And then 3 seconds later, it's at our final position. And that makes sense, right? You're just working out what that total angle is. And it's easy to use. It's super easy to use. Just the total angle divided by the total seconds. And again, in a real video, if you saw that it literally moved that angle in the first second and that angle in the second second and that angle in the third second, you have evidence that this thing is moving at a constant rotational speed, moving the same angle per second. All right, let's move on to the next idea, which is what about if there's rotational acceleration? Let's not do that. Well, we're going to do that, but just on the other side. Rotational acceleration versus, let's compare it to linear acceleration. Here's linear acceleration on this side. If someone said, what would you do with your videos on Pivot to actually prove that it's accelerating, you would motion map that, right? If it was, a puck going down a ramp, for example, and we saw this, it was here at 0 seconds, and then here at 1 second later, and here at 2 seconds, and here at 3 seconds. We'd say, aha, that thing is accelerating. I know that because the distance it covered in the first second is small, then the distance in the next second is larger, and the distance in the third second is larger, right? Distance increases each second, distance traveled, then it's accelerating. That's just easy to see on a video. That means it's accelerating. What would that look like on our wheel? If this thing is not going at a constant angular speed, but it's actually accelerating? Well, maybe it starts here, like we said, at 0 seconds. Maybe it still is here. at 1 second later into its rotation, but now it's over here at 2 seconds in its rotation. And now it's all the way over here at 3 seconds into its rotation. So that means in the first second, it went this distance. In the next second, it went this distance, angular-wise. And in the third second, it rotated even further in angle. That would be an immediate proof that this thing is accelerating. Because I can see it's not going through equal pizza slices. Before it looked like a pizza because they were all equal. But when you see it's not, this is somebody who's cutting small pieces and bigger pieces of pizza and larger pieces of pizza. That indicates this thing is, again, in a similar way to what's on the left of the board, gaining extra distance, but we'd say gaining extra angle per second. So let's go back over to here. We would usually say A is delta V over delta T in general for general idea of acceleration, linear case. What will it be for the rotational case? Yeah. You got it, yep. The new symbol, I will tell you, which you don't know yet, is alpha. Alpha is A. It's the letter A in the Greek alphabet. Physics has used the whole English alphabet. They've used the whole Greek alphabet. They might have dipped into other languages, I'm not 100%, because they just gobbled up symbols, well, they're letters. And after they finished our alphabet, they said, let's just grab another alphabet, and they started using other symbols. So when you see that's A, that's the Greek A, alpha. So it is the symbol for rotational acceleration. It's not random, right? It's A, it's their A. That totally is purposeful. Remember that V is like omega. Linear speed is like rotational speed. V is like omega. We just talked about omega. So this should say delta omega over delta T. So if I have a way of determining what the change in its rotational speed is and how long that took, technically I should be able to figure out what the angular acceleration is. Now let me make another idea here. Next idea. Now that's all I get to do today is just mostly ideas. Maybe one problem at the end, possibly. I hope so. Actually, yeah, you'll definitely get one problem in the end. Let's just say we were looking at T versus V for constant acceleration. And remember that constant acceleration doesn't just mean that something is constantly accelerating, which is true. It specifically means that it's gaining an equal amount of speed each second. And that's in physics called a constant acceleration. A falling rock is a perfect example. After 1 second, short of any air resistance effects, it would have a speed of 10 meters per second, 9.8. Let's just say 10. After 2 seconds of falling, the rock has a speed of 20 meters per second. After 3 seconds of falling, the speed at that 3 second moment is 30 meters per second. And it just keeps going up in equal amounts in terms of the speed. And yes, would we say it's constantly accelerating? Yes, but we're actually indicating that it's gaining an equal amount of speed each second. The amount it gains each second is constant, 10. Always 10 more in the next second. Called constant acceleration, right? So let's just make that point. This might be something that's falling again. You certainly could have, I'm pointing this out because in their AP exams, they might give you a data table. I mean, who knows what they're going to do? They could give you information in a paragraph. Sometimes if it's an experimental problem, they're going to show you a data table. And you would need to know that they're giving you the same information, just feeding it to you in different ways to see if you can interpret what you're looking at, regardless of the method they show it to you with. So if this was, something that was speeding up, maybe it's my washing machine, maybe, yeah, washing machines definitely speed up as they go into their spin cycle. We'd say that there's no rotational, no angle in the beginning. Then you press the start button on your washing machine and it starts rotating. Maybe, I don't know, maybe it's rotating at a rate of 10 radians per second. Again, you can think degrees per second. Think the angle per second. At the 1 second mark, that thing is rotating in that instantaneous speed of 10 radians per second. How long does it last with that speed? No time. It's only that speed at that exact moment in time. A millionth of a second later, it will be moving a little bit faster. So interestingly, the washing machine spends no time at any particular speed. And that's a really strange concept. I'm just pointing out it's an instantaneous speed at that instant. 2 seconds later, it would have a speed of 20 radians per second. And we would call this, again, a constant angular acceleration. If we said, what is it in a data table sense? You just pick 2 points, delta anything, it's final minus initial. You can pick any 2 points you want. You can pick the top 2. You can pick the first and the third. You can pick the first and the fourth one. It doesn't really matter which you pick. It's a constant rate. It's like a tree growing, 1 inch per year. Someone says, determine the growth rate. Here's a data table. 1 year later, it was 10 inches high. 2 years later, it was 20 inches high. 3 years later, the tree was 30 inches high. With this data, determine the growth rate. Well, you can reference the third year and say, okay, it grew 30 inches divided by 3 years. All right, 10 inches per year. You could have picked the first year and said, all right, it's 10 inches high divided by 1 year, 10 inches per year. It doesn't really matter, right, which point you pick, because this is a slope, right? Pointing out this is a slope. Just a reminder. Oop, good time to remind. Oop, oh, what happened? Good time to remind you of this idea that V versus T is linear, because the data that we're looking at is linear, and the slope, A is the slope. Same thing here. If we looked at they're going to potentially show you omega versus time graph for how quickly it's rotating, and they'd give you linear data. And you would need to know that alpha is the slope. So again, I could pick 2 points. It doesn't matter which 2 I pick. I'm going to pick this one and this one. So omega final would be the number 20. Omega initial would be the number 10. So I technically would do 20 minus 10 divided by delta t, the time interval in between 2 seconds and 1 second, 2 minus 1. So of course we'd get 10 radians per second is how much the speed is changing per second, right? It's changing by a rotational speed of 10 radians per second each second. You get to say second twice. Radians per second, which means the units are 10 radians per second squared. No different than, again, the acceleration is meters per second squared, because it tells us that it's gaining 10 meters per second of speed per second. And that turns out to be 10 meters per second squared, right? So there's that idea. Now, the next idea is just to point out that all of the formulas work. All of the formulas work. I'm going to try to go back. You can just replace all of the variables. Let's continue this. I guess I'm just finishing off my chart that I started with you. And you will see this exact same chart in your textbook. This is textbook. I'm teaching it in a textbook way. This is not very creative. This is the way that's done in a textbook, so you can see nice charts just like this. Alpha, which would be linear, get back. A, which would be linear acceleration. Linear acceleration, which is units of meters per second squared. And this would be alpha, which is rotational. Sometimes they use the word angular. Just want you to know that those 2 words are used interchangeably, angular and rotational acceleration. So, sorry about that. Acceleration. Yeah, messed that up. But that's the word acceleration. The units would be radians per second squared. So those are the 3 primary parameters that you use to track something's motion. Its position, How quickly the position changes, called speed, and how quickly the speed changes, called acceleration. Little louder? This one? Oh, this one? Yeah. Angular. So we are going to use the word rotational and angular interchangeably. So I'm just reminding you of that. And remembering that V is a rate, right? V is the rate that position changes. It's the rate at which position changes. It's how quickly your position changes. Oh, we call that velocity or speed. A is a rate. It's how the rate at which the velocity changes, how quickly your speed changes. So when you go down, these are rates, right? This is V is rate number 1. It's how quickly X changes with time, and then A is rate number 2. It's how quickly velocity changes with time. All right, so I'd lastly point out, we'll do one more example with you, and then you're going to try some things. Let's try the position formula. Can we still use it? I promise you, you can use all of the equations you've already learned, because otherwise you'd be thinking, oh my God, is there a whole other slew of equations we have to learn? No, you've noticed that they all mirror each other. You just take away one symbol and you stick the other symbol in. Let's try. You can try it. Let's try to rewrite this and let's just, before we do that, let's remind ourselves what this means. It means that if you have some position that you're calling, x equals 0, let's say here, and you have a car that starts over here, we call that x initial. X initial is the position at 0 seconds. And is it moving? I don't know. If it starts at rest, the initial is 0. If it's already cruising along and it already has some initial speed, like 5 meters per second, then I'd have to plug in the number 5 there. If the problem gives me the acceleration and says the car's acceleration is the number, I don't know, so 6 meters per second squared. The initial speed is 5 meters per second. And the initial position is, I don't know, I'm just making this stuff up, 20 meters. So a car is moving along and it starts at the 20 meter mark. At that moment, it already has a speed of 5 meters per second, and it's gaining 6 meters per second of speed each second. Determine how far away it is from the 0 mark 10 seconds later. We'd say, okay, this is really a function of time, right? X is a function of, this is like X in math class. The other things are just constants. X initial is a constant, initial position, that doesn't change. V initial is just a constant, it's what speed it had in the beginning, doesn't change. A is just a number, it's a constant acceleration, it's number 6. Remembering that the only things like in math class where we have Y's and X's, this is our Y and these are our X's, right? So if I were to create this formula, I'd say, all right, X initial was 20 plus 5t plus 1/2, the acceleration is the number 6. And then I'd write t squared here. Right, and technically I could write that out and simplify it, 20 plus 5t plus 3t squared. It's a polynomial, it's the quadratic, all that sort of stuff from math. Yeah, but whatever. Anyways, you can create a formula that would then be used. If someone says, how far away is it 10 seconds later? Well, we would use that formula. X evaluated at 10 would be 20, just reminding you, plus 5 times 10 plus 3 times 10 squared. And I don't know what the answer is. I don't even care. The point is I could add it up. I could do it on a calculator and blah, 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 blah. Okay, 1,200. So that means this position of this car is 1,200 meters away 10 seconds later. Just reminding you how we use that. Now we're doing the same thing, saying, can we actually predict where something is along the circle if we know where it starts, its initial angular position, how fast it's rotating in the beginning when we start watching it, that would be omega initial. And if we know what its angular acceleration is, alpha, should we be able to, in theory, again, if a clothes stuck on the side of the washing machine starts here, and we know, again, maybe the initial speed is 0. We'll cross the second term out. You've seen that a million times. Maybe x initial, that's like the angle initial, maybe that's 0 degrees. It's like saying the car starts at rest, or with 0 on the starting line of 0 meters. X initial gets crossed out, V initial gets crossed out. For our rotation scenario, that means theta initial is 0. Omega would be the next one, initial crossed out. You technically could build a formula and then use the formula to predict where will this piece of clothing be as it starts rotating faster and faster and faster 10 seconds later. So see if you can build that formula. In fact, I'm going to see if you can build all of them. Reference all of the kinematic equations you have in your brain. And I'll tell you these are them, and just recreate them. You can, again, you are not learning new equations. You are using the exact same equations. You are taking away one of the variables from the chart that I started showing you and plugging in the analogy symbol. For example, again, take away x, put theta there. When you see a v, take it away, put an omega there, the W sign. When you see an a, take it away, put an alpha there. You're rebuilding the same formula just with different symbols in reference to predicting, rotation speeds or rotational positions or whatever it might be. Give it a try. This is exactly what's in your textbook. It's taught the exact same way. Give you a few minutes to try that, and then I'll give you an example problem that you can try. If you feel like overwhelmed that it was a lot of new stuff, trust me, after teaching AP a while and not long enough to know that students get comfortable with this pretty quickly. Because once, right, Joey? I mean, once you recognize, yeah, this is all the same stuff, actually. It's all the same formulas, it's all the same ideas. I just have to think in circles now. It normally comes after a week or so. People are pretty comfortable with it. So just trust what I'm saying is true. Yep, totally. Absolutely. Thank goodness, because otherwise, boy, if you had to learn all new stuff, like all new equations, like, oof, that'd be a lot. And actually, while you're doing that, keep going. I'm going to make a little problem for you to try. Let's go to here.
Pretty good. Circle.
Yeah, I like my circles. I'm practicing my circle. There was one year where it was almost perfect. And I'm not trying to pat myself on the back, but you brought it up. I can't help but remember there was one year I went like this and someone was like, oh my God, it looks perfect. And so he wanted to come up and measure it. So he started measuring it from the center.
I think that might have been.
Would have been with you. And it was almost within like all the radius measurements within a tiny, tiny fraction of each other. It was almost a perfect circle. Yeah. You got to keep your elbow still and use it kind of like a compass. You put the thing, you spin it around like this. And yeah. I know. Well, when you've been drawing circles for 15 years, trust me. Okay, so let's, you keep going with that, and I'm just going to make a problem for you to try. Oh, no. No, right there. Okay, I'm going to actually pop back over to this in a second. I'm just going to remind you that, again, these, you had some time to try it. These formulas, when rewritten, are like this. Because again, you take away V and you put omegas. You take away A's and you put alphas. So that means our old one for maybe calculating the final velocity after accelerating for some seconds, we could use it to this one now to calculate the final rotational speed after accelerating in a rotational sense for some amount of seconds. And then any of the ones that we had before on the board that I might have erased. The position formula. Again, X is now like theta, V is like omega, A is like alpha. And then you have your, slope form kind of delta V over delta T, which would have been, which would be alpha is delta omega over delta T. And just know that this is your toolbox for solving a lot of word problems. Or V is delta X over delta T. That one would be omega equals delta theta over delta T. So that's the analog. When we say analog, meaning the thing that's an analogy to something else called the analog. So all the linear terms with their analogs next to them for rotation. And I know that looks like a lot to look at, so I'll put a box around these. This is your toolbox. It's the same exact formulas, just written with new symbols for a new application. 1, 2, 3, 4, 5. You can pretty much solve any kinematics problem with those 5. Does anybody want me to leave this on here for a second? All right, well, you can try your problem. Where is it? Here it is. We're looking at a disc. I mean, it could be a saw. They reference grinding wheels in textbooks. A grinding wheel is like a sanding wheel that spins in the shop class. You turn it on, things start spinning. You hold your wood up against it to sand. Called the grinding wheel. Again, who really cares about keeping track of a piece of tape on a grinding wheel? Nobody does, right? It's not the point. We're trying to just teach students how do you handle things that are rotating. It can be machines that people are building. It can be, asteroids rotating as they tumble through space. There's, probably millions of different applications in science of engineering, even atoms themselves called rotational energy on an atomic scale in chemistry. There's many applications. So just know that we're teaching you just the general format of how you deal with anything that's rotating. What the object is doesn't really matter. We're just teaching you the structure. So a grinding wheel starts at rest. I drew a picture of it with a piece of tape at the 45-degree mark. Again, in the next class and beyond that, it's all radians. Once I've taught you radians and everything's radians. For today's, it suffices. We can use degrees, not a big deal. The grinding wheel starts at rest with a piece of tape on it, and you can see that piece of tape right here. And it's starting at the 45-degree mark. When it is turned on, it has a constant angular or rotational acceleration of alpha equals 50 degrees per second squared. And I want to point out, that means that omega increases, the rotational speed itself increases by 50 degrees per second each second. Reminding you, like if I said, the Ferrari has an acceleration of 20 meters per second squared, that means after 1 second, its speed will be 20 meters per second. After 2 seconds of accelerating at that rate, the car's speed would be 40 meters per second, and then 60 meters per second. Reminding you that same concept applies. You're seeing different units, and it can become uncomfortable or unfamiliar, but reminding you when I say alpha equals 50 degrees per second squared, that means the rotational speed is increasing by an amount of 50 degrees per second each second. So the first question is at the top. What is the total angle the piece of the tape has rotated through in 10 seconds? That's like saying, how far away is the car 10 seconds later? If it started at rest and we gave you the linear acceleration of the car, and we told you that the initial position of the car was 5 meters, calculate the final position of the car 10 seconds later. The same problem, just in the rotational sense. We have an initial position that's given. We have an angular acceleration that's given. We have an angular speed that's initially 0. And we look through our toolbox and think, poke around at them and think, I wonder which one I could use to solve for the total angle. Remember, angle is now theta. And it definitely has to be a formula that incorporates all of the things that were given. It has to have alpha in it, theta initial, theta final, because that theta final is the final, that references the final angle, theta final. So the formula would have to have theta final in it, theta initial in it, alpha in it, omega initial in it. You have to have all those things. Omega initial actually is 0, but we still have to have all of those things in it. Once you feel like you have it, plug them in and see if you can solve it. Question B, I guess I'll write up here. How many full rotations did it complete? It being the tape. Question B is on the other side. And I guess one more, question C. So the last question is there as well. A, B, I kind of went, I guess, started on the top left, then to the top right, and then underneath, A, B, and C. Just remember that you get points for writing the formula down. Usually, you often get some sort of points for some sort of numbers, something with numbers, like showing substitutions, usually. And then, they reference the answer, they reference the unit. So you always want to be in the habit. Many of you are. I'm just being honest. It's not all of you. There's a handful of students in this 15-person group that still go straight to numbers. I look at your homework, and there's numbers all over the place. I don't see any equations. I don't see any letters. It's numbers everywhere. And in a lot of cases, that's actually correct. You're calculating it correct, but the AP exam will end up docking points from you for not showing certain things, like not showing your equations and stuff.
Part A, B, and C, and you have 9 points. A was 1, B was 1, 6 points. On part C, you got 4 out of the 6 points that any computation.
There you go.
I mean, one of the points on part C, all you have to do is write B plus C at the end of it, just for that.
Yep.
Like
That's how they grade it, though.
That's 1%.
Because they're trying to make it so that kids that get wrong answers can still potentially get a lot of the points, right? They don't want it to be like, well, you all fail because, only 10% of the population got it all right. I mean, yeah.
7 out of the 9 points.
Yeah, absolutely. Yep. They give away points for what you show. again, just a reminding that everything in the next class will be radians. I'll teach you about radians. They probably won't. The only mention they make of degrees on the AP exam is if they do projectile motion and they say, well, that's not true. What am I saying? There's many mentions of degrees, ramps and all that stuff. It's all degrees. But as soon as they give a question that's referencing rotation, they're not going to say degrees at all. It's always radians. So I definitely will provide you with that lesson first thing the next time I see you.
I just finished up my last unit, reading my last unit, so I'm all set now. Just got a review, work on some practical response, practical features.
Final stretch.
Yep, final stretch.
It's always a good feeling.
Yeah. So I just wanna do some practice questions on. I just finished reading reputation. So I'll do some practice questions on that, and then next week I'll start reviewing.
Nice. Good for you.
Yeah.
Coming up relatively soon now. You got 6 weeks. I'll be surprised if you don't get a 5, to be honest. If you don't, I mean, you don't, but
Yeah.
if I was a betting man, and I'm not, I don't bet. I never bet. The odds are always against you if you bet. You'll always lose your money. I'm going to tell you, don't bet. Don't gamble. It's not worth it. Unless it's like a once in a blue moon thing. But anyways, if I was a betting man, I'll bet that you get a 5. And what's going to help you the most is what you did in my class. Because all the concept you got to bring forward. You got to layer in the math stuff you were learning from math class, but all the conceptual stuff still held to be useful, very useful during that course. It's all the same topics.
And I was just reading practice multiple choice questions a few minutes ago. Not only is it questions from AP1, but there's also some questions that are purely just calculus. And there was one question, it was a multiple choice question of like x equals 5 times sine of 2 pi, and then y equals 5 times the cosine of whatever, and then the question was, what is the radius of this circle? And I'm like, well, I know the formulas are cosine theta and r sine theta, so radius would be that.
Huh.
that. Right, yeah. So
Totally.
like
Yep.
that's just, I know that from doing polar equations.
Oh yeah. Yep.
I mean, that's it.
Yeah.
And you can use your calculator too.
I know. And they don't.
Like I read that and I was like,
They don't limit it at all. Like you can literally put anything you want into that calculator.
You can put.
Yeah.
I was like, what's preventing somebody from just putting those 2 equations into the calculator?
Nothing. Nobody's going around checking either. I'm not saying you should do that. I'm just letting you know they don't. I mean, they couldn't possibly monitor that. Not to mention with kids taking it at home this year. No way. All right, guys. There's only a couple of minutes left. This is part of your homework, not surprisingly. I'm also going to probably either choose something for you to do in CK12 or straight from the textbook, not both. I'm going to probably lean towards the textbook because the textbook is really good with images and formulas and more of the complicated stuff. Textbook does a better job than CK12. More of the concept stuff, I think, comes better from CK12. But I taught you a lot of the concepts today. So I think I might give you some sort of exercise or reading and maybe a couple problems from the textbook, but I'll post that for you guys. But in addition to this problem, and that'll be due on Thursday. And I mean, might throw out there, anybody who likes robots, like there's plenty of gears turning on robots. If you want that stuff to all work properly, if you were engineering something, you would need to know all of this stuff. about how gears turn, at certain rates, and have to engage with certain levers and all that sort of stuff. Like this, for mechanical engineers, especially people who get into robotic stuff, this is very useful. I mean, you might not recognize that right now, but it is. All right, guys at home, any questions at all? If I can try to find you. Let me see. Yeah. Any questions at all, guys, at all? Girls, I should say, two of you. Any questions? You have a good day today? That's good. That's good. All right. I mean, because I think we're out of time, right? Yep, it's 1:40. All right, you guys have a great day. I'll see you later. Let me know if you have questions about the assignment. Just know I'm going to post a little extra stuff on Google Classroom. All right. Okay. Bye-bye. All right. That's right. You weren't seeing me. Now you see me. Bye. Bye, guys, girls. Okay. Do you guys have any questions at all? No. Okay.